Hello and welcome. Today we're going to talk about quantum mechanics, but not in the way you might be used to. This isn't a philosophy lesson, and we're not going to dive into the weirdness of the quantum world. Instead, we're going to strip it down to its core mathematical foundation. Quantum mechanics isn't weird. What's weird is how badly it's often taught. If quantum mechanics feels mystical, confusing, or philosophical to you, I promise you that's not physics. It's almost certainly a linear algebra problem you haven't fully understood yet. My goal today is to convince you that by the end of this video, you'll understand why almost every confusing aspect of quantum mechanics is just linear algebra in disguise. We'll clarify exactly which concepts matter and which ones you can safely ignore for a while. To do this, we'll break it down into 5 key ideas. Let's start with the most fundamental concept of all. Our first topic is that in quantum mechanics, the state of a system is a vector. This is the most crucial takeaway. In quantum mechanics, a system isn't described by a single number, like its position or its energy. Instead, it's described by a vector. A quantum state lives in a complex vector space. We represent these state vectors using a special notation called a ket, which looks like this. Let's be clear about what this means. Imagine a simple system, like a coin that can be in one of two states, heads or tails. In quantum mechanics, we represent these as two orthonormal basis vectors. Let's call the head state Gusso and the tails state R1. Just like any vector in a 2D space can be written as a combination of basis vectors, I and j, any quantum state of this coin system can be written as a combination of these two basis vectors. So, a general state, POPs, is a complex linear combination of these basis states. Equals some complex number C0 times A0, plus another complex number C1 times A1. This equation, the core of quantum mechanics, is simply a vector addition. Superposition isn't some mystical simultaneous existence, it's just vector addition. In this state, the coin isn't heads or tails, just like the vector 3i plus 4j isn't purely on the x-axis or the y-axis. It's a combination. It's the probabilities of finding it in either state that matter. Let's look at a few examples to solidify this idea. Let's work through our first example. Consider a particle's spin. Spin is an intrinsic property of a particle, and along any direction, it can only be measured as up or down. We can define a basis using two orthonormal vectors. Let's call the spin-up state and the spin-down state 1. So, any possible spin state of this particle is a vector in a two-dimensional complex vector space. A general state, Dieshevs, can be written as a linear combination of these basis states. Equals a coefficient alpha times A, plus a coefficient beta times N. Here alpha and beta are complex numbers. A key rule is that the state vector must be normalized. This means the square of its length must be 1. The norm squared, or the inner product of the state with itself, must be 1. This leads to the condition that the magnitude squared of alpha plus the magnitude squared of beta must equal 1. This condition ensures that the total probability of finding the particle in any state is 1. So, for example, a valid state could be 1 over the square root of 2 times and plus I over the square root of 2 times. If you square the magnitudes of the coefficients, you get 1/5 plus 1/5, which is 1. This is a vector representing a superposition of spin-up and spin-down. Again, this isn't magic. It's a fundamental consequence of using vectors to describe physical reality. For our second example, let's consider the polarization of a photon. A photon can be linearly polarized along a vertical or horizontal axis. So we can use a basis of two orthonormal vectors. Our V for vertical polarization and H for horizontal polarization. A general state of polarization can be expressed as a linear combination of these basis vectors. The coefficients tell you how much of each type of polarization is present. So Saspa Basti equals C phi times Vav plus Sich times H, where C phi and Sich are complex amplitudes. Now let's consider a photon that is right circularly polarized. How would we write that as a vector? It turns out the state for right circular polarization can be written as 1 over the square root of 2 times quite plus I over the square root of 2 times V. This is just a vector. This state is normalized because the sum of the squared magnitudes of the coefficients is 1/4 plus 1/5, Why? What if we use a different basis? Instead of vertical and horizontal, we could use a diagonal basis, defined at 45-degree angles. Let's call them bash D for diagonal and NA for anti-diagonal. The states for diagonal and anti-diagonal polarization can be written as vectors in our original basis. D is a superposition of H and THV. Similarly, H can be written as a superposition of qubits and Hi. This demonstrates that our choice of basis is arbitrary, but the state vector itself is what's physically real. It's just a vector, which can be represented differently depending on the coordinate system we choose. Our third and final example for states as vectors is the position of a particle. This takes us into a continuous vector space. In this case, the basis vectors are not discrete. Instead, we have a continuous set of basis states, which we label with a position coordinate, say x. We can think of the ket black as a vector representing a particle being precisely at position x. A general state of a particle is still a vector, but now it's an infinite superposition of all possible position states. We represent this as pots equals the integral over all x of a complex function plus cx times x. The function plus x is our new set of coefficients. The vector space is now infinite dimensional. This might seem more complicated, but the core idea is the same. Psis x is a vector component. But for a continuous index x, instead of a discrete index like 0 or 1, let's consider a simple example, a Gaussian wave packet. This represents a particle whose position is not precisely known, but is localized around some average position, x0. This state is represented by the function plus x. Notice that the particle's state isn't a single position x, but a vector in an infinite dimensional space, where its components are given by the wave function. The wave function is just the components of the state vector in the position basis. The normalization condition for this continuous case is that the integral of the magnitude squared of psi x over all space must equal 1. This ensures the total probability of finding the particle somewhere is 1. So, we've seen that quantum states are just vectors, whether in 2 dimensions or infinite dimensions. The weird part, superposition, is just the familiar concept of vector addition. Our second major topic is that every measurable quantity in quantum mechanics is represented by a matrix. These are called observables. Think about a classical system. You can measure its energy, its position, or its momentum. In quantum mechanics, these aren't just values that exist independently. They are operators, which act on our state vectors, psi. Every physical quantity that can be measured is an operator, represented by a matrix, say a hat. These operators act on our state vectors, plus. Physics in this view is the study of how these matrix operators transform our state vectors. No matrices, no physics. Let's revisit our simple coin or two-state system. For this system, any observable must be a 2x2 matrix because it acts on 2 component vectors. A very important set of observables for a two-state system are the Pauli matrices. They are the fundamental operators for systems like electron spin or photon polarization. Let's write them down. Sigma x is 0, 1, 1, 0. Sigma e is 0, negative II 0. And sigma z is 1, 0, 0, negative 1. These matrices correspond to measuring the spin along the x, y, and z axes, respectively. Let's see what happens when they act on our state vectors. Let's work through our first example of an observable acting on a state. We'll use the Pauli z matrix. Our operator is sigma z, and we'll apply it to a general spin state base Shikai. We'll write the vectors as columns in the spin-up, spin-down basis. The action of the operator is just matrix multiplication. Sigma z acting on pops is the matrix 1, 0, 1 multiplied by the column vector a, 5. This gives us the new vector a, ba. This is a new vector. The operator sigma z transformed our original state vector into a different vector. For a second example, let's consider the Pauli x operator. Our operator is sigma x, and we'll apply it to the same general spin state. Again, it's just matrix multiplication. Sigma x acting on kashapas is 0, 1, 1, 0 times a v. This gives us va a. This operator, which represents a measurement of spin along the x-axis, flips the coefficients of the spin-up and spin-down components. It transforms the state vector. As a third example, what happens if we apply sigma z again to the state we got from the first example? Sigma z acting on A gives us AV. This is our original state vector. This means that applying sigma z twice brings the system back to where it started. This behavior is a property of the specific observable. Sigma z squared is the identity matrix. Physics is all about these matrix relationships. We've established that states are vectors and observables are matrices. Now for the core idea of this entire video, quantum measurement is just an eigenvalue problem. This is where the weirdness usually kicks in, but it doesn't have to. When you perform a measurement on a quantum system, you are essentially asking a mathematical question. Which eigenvalue does this operator return? In linear algebra, we know that there are special vectors called eigenvectors. When an operator acts on an eigenvector, the result is the eigenvector itself, just scaled by a number. This is the famous eigenvalue equation. A hat acting on Xiaoshuv equals lambda times v is the eigenvector, and lambda is the corresponding eigenvalue. In quantum mechanics, this equation takes on a profound physical meaning. The eigenvectors of an observable operator, matrices, are called the eigenstates or basis states, and their corresponding eigenvalues, lambda, are the only possible results you can get when you measure that observable. Let's repeat that. The eigenvalues of the operator are the only numbers that can ever appear on your lab equipment screen. And once you measure a specific eigenvalue, the system's state collapses into the corresponding eigenvector. If you understand eigenvectors, quantum measurement stops being scary. It's just a property of matrices. Let's find the eigenstates and eigenvalues for our Pauli's observable. For our first example, let's find the eigenstates and eigenvalues of the Pauli Z matrix. This corresponds to measuring the spin along the z-axis. Our matrix is sigma z, and we want to find its eigenstates and eigenvalues by solving the equation sigma z acting on an unknown state. X equals lambda times chops. In our basis of h and k, the equation looks like this. We're looking for a vector with components a and v, and a number lambda, that satisfy this matrix equation. Solving this, we find two possible eigenvalues. The first eigenvalue is lambda equals 1. The corresponding eigenstate is 1, 0t, which is just our spin-up state. This means that if you measure the z-spin and get a value of +1, the particle is now in the spin-up state. The second eigenvalue is lambda equals 1. The corresponding eigenstate is 0, 1t, our spin-down state. So if you measure a z-spin of 1, the particle is now in the spin-down state. This perfectly matches our physical intuition. For a z-spin measurement, you can only get +1 or 1. These are the eigenvalues of sigma z, and the measurement leaves the particle in the corresponding eigenstate. Now for our second example, let's look at the Pauli X matrix. This represents measuring the spin along the x-axis. The process is exactly the same. We take our matrix, sigma x, and solve the eigenvalue equation. Solving this equation gives us the eigenvalues and eigenstates for an x-spin measurement. The eigenvalues are +1 and -1. Notice they are the same as for the z-spin. The physically allowed values are the same, just for a different axis. But what about the eigenstates? They must be different vectors. The eigenstate for x spin up is 1 self times up plus d. The eigenstate for x spin down is 1 c times t. These are superpositions of our z-spin basis states. This gives us a deep insight into why measuring x spin is incompatible with measuring z-spin. The eigenstates for sigma x are not the same as the eigenstates for sigma z. They form two different, equally valid orthonormal bases for the same vector space. This is the source of the Heisenberg uncertainty principle. When you measure z-spin, the state becomes an eigenstate of sigma z. This state is a superposition of the eigenstates of sigma x. If you then measure x spin, the system has no definite x spin. There is no state vector that is simultaneously an eigenstate of both sigma x and sigma z. It's a statement about the vectors, not about a particle choosing. Our third example of measurement as an eigenvalue problem takes us to continuous systems, like position or momentum. In this case, our matrices become operators that involve calculus. For position, the operator x hat is simply multiplication by x. For momentum, the operator p hat is negative ih bar times the derivative with respect to x. The eigenvalue equation becomes a differential equation. For position, the equation is x times pla x equals lambda times pla x. The only solutions are highly singular functions called Dirac delta functions, which are just fancy names for the position eigenstates E. For momentum, the equation is negative I h bar times the derivative of psi of x equals p times p psi of x. The solutions are complex exponentials. These are the momentum eigenstates. The fact that the eigenvalues for momentum, p, can take any real value is why we can measure any real value for a particle's momentum. But it's still an eigenvalue of an operator. The principle is the same as with 2x2 matrices. So, to recap this crucial section, measurement is finding eigenvalues and eigenvectors. The eigenvalues are the possible results, and the eigenvectors are the states the system is forced into. We've established that the outcome of a measurement is one of the eigenvalues. But what determines which one? This brings us to our fourth point. Quantum probability is geometry. Let's say our quantum system is in a general state, PUPS. We want to measure an observable A hat. We know the possible results are the eigenvalues lie, and the system will end up in the corresponding eigenstate phi. So our initial state P is a superposition of all possible outcomes. This is like a vector pointing in some direction in a multidimensional space, and the eigenstates phi form an orthonormal basis for that space. Think of it like this. Measurement is projection. Measurement is projection. When you measure the observable A hat, you are projecting the state vector plops onto the eigenstates phi. The coefficient, or amplitude c, for each eigenstate phi is not some random number. It's the projection of the vector sot plots onto the vector phi. We calculate this with an inner product. The complex number ci is the inner product of phi with plus. It tells you how much of the eigenstate phi is contained in the state plus. This is nothing more than a dot product. In a real vector space, the dot product gives you the magnitude of the projection of one vector onto another. And here's the magic, which isn't magic at all. The probability is the square of the magnitude of this projection. The probability of measuring the eigenvalue lie is the squared magnitude of the amplitude CIP equals GC2, which is equal to the squared magnitude of the inner product of phi with plots. So, quantum probability doesn't come from randomness. It comes directly from the geometry of the state vector in the vector space, specifically its projection onto the different eigenstate basis vectors. Let's apply this to our spin example. Suppose a particle is in a state CPD itzel 1 sapasas plus I2. This state vector can be visualized. The amount of the Cauchy basis vector is 1/2 alpha, and the amount of the Cauchy basis vector is I2. What is the probability of measuring z spin up? First, we find the eigenstate for z spin up, which is y. The probability is the squared magnitude of the inner product of y with our state, pups. We substitute our expression for hash pups. The inner product is linear. The inner product of phi with I is 1 and with wa is 0. So we get 1 tulpa plus 2, which is 1/2. The probability of measuring z spin up is 1/2 or 50%. Now let's find the probability of measuring z spin down. This is the squared magnitude of the inner product of xiao with plus. Performing the same calculation, the inner product of hap with v is 0 and with d is 1. We get y22, which is also 1/2 pt. So our vector piece represents a 50-50 chance of measuring z spin up or down. Geometrically, this means our state vector pus is halfway between the z spin up and z spin down basis vectors. That's it. For our second example, let's take the same initial state and ask a different question. What is the probability of measuring x spin up? Our state is the same as before. Our question now involves the sigma x observable. We need the eigenstate for x spin up, which we previously called. The eigenstate is 1 over the square root of 2 times h plus. Now we calculate the probability using the inner product. The probability of finding the particle in the x spin-up state is the squared magnitude of the inner product of how with plus. We substitute our expressions for both vectors. Since the eigenstate involves complex conjugation, we write the bra. We distribute the terms, which gives us 4 inner products. Using the orthonormality relations Gauss each 1 is 0, or 0 has the 1, the expression simplifies to a half times 1 plus I. Squaring the magnitude of this complex number gives us 1/2, 2 equals 1. The probability is 1 or 100%. Wait, I made a mistake. Let's recheck the calculation. The bra corresponds to the vector 1, 2, half. So, x is 1/2 1/2 plus 1 I2, which is 1 2 1 ply. The magnitude squared of this is 1/2, 1 plus I2 equals 1 4. 12 plus 12 equals 1 4. 2 equals 1/2. My apologies. The probability of measuring x spin up is 1. The probability of measuring x spin down is also 1/2. The lesson here is still valid. Even if a calculation is tricky, it's still just linear algebra. The probability of measuring a certain value is always the squared projection of the state vector onto the corresponding eigenstate. Our third and final example for probability takes us back to our continuous wave packet. Remember our Gaussian wave packet localized around position x0. We describe this as a state vector psi plus in a continuous vector space. Gaussian wave packet centered at x0. What is the probability of finding the particle in a small region of space, let's say between x and x plus dx? The eigenstate for a particle being precisely at position x is just the ket kata x. The probability density is the squared magnitude of the inner product of x with our state qubits. The probability density pk is the magnitude of the inner product of x with saki squared. The inner product x odd plus in the position basis is simply the wave function plus x. So the probability density p dipax is just the magnitude squared of the wave function plus. This tells you the likelihood of finding the particle near position x. The probability of finding the particle in a finite interval is the integral of this probability density. The probability of being between a and b is the integral from a to b of the magnitude squared of the wave function. This should look familiar. The integral of Gauss 2 over all space is 1, a statement of normalization. This is why we call plus x the probability amplitude. Its magnitude squared gives the probability density. Again, this is geometry. The probability comes from how much the state vector Sallas overlaps with or projects onto the eigenstate A. Our final topic for this video is how quantum states change over time. This is described by the Schrödinger equation, which is nothing but a linear systems theory problem. The time-dependent Schrödinger equation, in its most general form, looks like this. It relates the time derivative of the state vector dpups dt to the state vector itself through an operator called the Hamiltonian h-hat. In quantum mechanics, the Hamiltonian h-hat is the operator for the total energy of the system. It's an observable, and it's a matrix. This is a first-order linear differential equation. It's just like the equations engineers solve every day to describe how systems change in time. The general solution to this type of equation is an exponential. The state vector at any time t, pop-c, is found by multiplying the initial state pop0 by this operator, e to the power of negative ih hat t over h bar. What is an exponential of a matrix? It's defined by a Taylor series, just like the exponential of a number. The matrix exponential e to the power of some matrix A is the identity matrix I plus A squared over 2, and so on. This is a fundamental concept in linear algebra and differential equations. Quantum dynamics is nothing more than this. Quantum dynamics is matrix exponentials. Engineers do this every day. Let's apply this to a simple but fundamental quantum system, a particle in a box. The energy levels for a particle in a box are discrete. Let's assume our system starts in an initial state, such. We can always express this state as a linear combination of the energy eigenstates in. The energy eigenstates on are special because they are also eigenstates of the Hamiltonian. The Hamiltonian h-hat acting on an eigenstate gives the eigenvalue En, which is the energy of that state times 1. This means that if a system is in an energy eigenstate, Its energy is perfectly well defined and its state doesn't change over time, except for acquiring a phase. If we apply the time evolution operator to an eigenstate Slan, because h hat is diagonal in its own eigenbasis, we simply replace h hat with its energy eigenvalue En. The state remains enum, but it gets a phase factor e to the power of negative I key in t over h bar. Now let's see what happens to our initial state, psu0. The time-evolved state, post, will have each of its energy components evolve independently, each acquiring its own unique phase factor, e to the power of negative IENT over h bar. This is just applying a diagonal operator to a vector expressed in the eigenbasis of that operator. Each component is scaled by a complex exponential. This is why superpositions of energy states can evolve in complicated ways, but it's pure linear algebra. Our second example of time evolution is for a two-state system, like our spin 1/2 particle in a magnetic field. The Hamiltonian, which is the energy operator for a spin in a magnetic field, is given by negative gamma times the inner product of the magnetic field vector B with the vector of Pauli matrices sigma. In the Z basis, this is a 2x2 matrix. Let's say we prepare our particle in the spin-up state. At time t0, the time-evolved state is given by the matrix exponential operator e to the power of negative IH hat t over h bar applied to the initial state. Calculating this matrix exponential is the entire problem. The Hamiltonian h hat is unobservable, so we know we can diagonalize it. If we write our state and Hamiltonian in the eigenbasis of h hat, the matrix exponential becomes very easy to compute. We just replace the Hamiltonian with its eigenvalues. Let's consider a special case where the magnetic field is along the z-axis. The Hamiltonian becomes proportional to the sigma z matrix. In this case, the Hamiltonian is h hat equals some constant omega times sigma z. The eigenstates of h hat are just alt and psi with eigenvalues h bar times omega and negative h bar times omega. Since our initial state is an eigenstate of this Hamiltonian, its evolution is simple. The time-evolved state is simply the initial state, multiplied by a time-dependent phase factor. The physical state doesn't change, only its mathematical representation. This phase factor has no physical effect. It's just a rotating vector in the complex plane. This is why a spin-up state in a Z field remains spin-up. Our final example of time evolution shows how a system can change its state. Let's place a spin-up particle in a magnetic field that points in the x direction. The Hamiltonian is now proportional to sigma x. We start in the Haas state. Unlike the last example, our initial state is not an eigenstate of h hat equals osa x. Remember, the eigenstates of sigma x are sapost and sid. First step, write the initial state as a superposition of the eigenstates of the Hamiltonian. Our initial state can be written as 1 over the square root of 2 times the x spin up state plus the x spin down state. Now we apply the time evolution operator. It acts on each term in the superposition independently. The time-evolved state is 1 over the square root of 2 times the time evolution of ad plus the time evolution of hu. Since and are eigenstates of h hat, they just pick up phase factors. So we get 1 over the square root of 2 times e to the power of negative I omega t plus e to the power of positive I omega tl. This is a superposition of the two eigenstates with time-dependent complex amplitudes. This describes Larmor precession, where the spin vector rotates around the x-axis. At time t(a) 2o, the state becomes 1 over the square root of 2 times plus times a phase factor. This is precisely the Quabard state again. No, wait, if t c2co, then ott pa 2. So we have e to the power of negative ip2, which is I, and e to the power of positive ip2, which is I. This gives us I plus I, which is I, 1 tu, plus I, e into e I. This is multiplied by I. It is physically the same state. My apologies again for the calculation error. Let me use a simpler example. Suppose at t=0, a particle is in the heat state t. What is the probability of measuring it to be tikao at time t? We calculate the probability, which is the squared magnitude of the inner product of zas with the time-evolved state. This is the magnitude squared of the time-dependent phase factor, which is always 1 times the inner product Qatar squared. That inner product is 1/2, and its square is 1/2, so the probability is always 1/2. This is the correct calculation. So we've seen that the dynamics of quantum systems, from particles in a box to spins in a magnetic field, are just applications of linear algebra. They are solved by finding matrix exponentials, which are fundamentally about finding the eigenvectors and eigenvalues of the Hamiltonian. There is one more crucial linear algebra concept that is often considered the source of quantum weirdness: entanglement. But it's just what happens when vector spaces get big. Entanglement isn't magic. It's a direct consequence of how we describe systems with multiple parts using tensor products. Let's consider two quantum systems, System A and System B. Let's say System A lives in a vector space VA, and System B lives in a vector space VB. To describe the combined system, A plus B, we don't just add the vector spaces. That would make the dimension the sum of the individual dimensions. Instead, we use the tensor product. The state space for the combined system, HAB, is the tensor product of the individual state spaces, HA and HB. What does this mean for the dimension? Tensor products don't add dimensions, they explode them. If System A is in an n-dimensional space, and System B is in an m-dimensional space, the combined system is in an n times m-dimensional space. For example, if System A is a spin 1 cephus, 2 dimensions, and System B is another spin 1 cephu, 2 dimensions, the combined system needs a 2 times 2 or 4-dimensional vector space to be described. Most quantum weirdness, like entanglement, arises because we try to understand high-dimensional linear algebra using our 3D intuition. This is a crucial distinction. Let's work through an example of a composite system. Imagine two coins, which we'll call coin A and coin B. We can define a basis for each coin. For coin A, let the head state be YARHA and tails TA. Similarly for coin B, the state of the combined system lives in a 4-dimensional vector space. The basis vectors are the tensor products of the individual basis vectors. The basis states are AHA, HB, which we can shorten to HH, HA, OTB, or OHT, TTHB, or TATI, and TTTPC, or TT. These 4 states form an orthonormal basis. Any state of the two-coin system can be written as a linear combination of these 4 basis vectors. A general state OPS equals a coefficient CHH times HH, and so on. This is a 4-component vector. Now, a separable state is one that can be written as the tensor product of a state of System A and a state of System B. For example, the state RHA, 2 ate, tensor product TB is a separable state. This is just a vector that points in a very specific direction in our 4D space. When you measure a property of coin A in a separable state, the result is independent of coin B. This all follows from the rules of linear algebra. Tensor products give us a way to describe two systems simultaneously. Now, let's explore what happens when we create an entangled state. An entangled state is a state of a composite system that cannot be factored into a tensor product of states of its individual components. This means that no matter how you try, you cannot write an entangled state as the product of a state of System A and a state of System B. Let's take a classic example known as a Bell state using our two spins. The Bell state FF plus is 1 over the square root of 2 times AH plus. Can we write this as a product of two single spin states? Suppose it could be. Let pops A equals A plus B and pop B equals C plus D. Their tensor product gives A plus D. This is a general state with 4 components. To match our Bell state EF plus, we would need to find constants A, B, C, and D such that AD and BC are both 0. This implies that at least one of the pair AB must be 0, and at least one of the pair /D must be 0. For example, if B is 0, then a chi. This would mean that both FA and FB would be pure basis states like WAC or HA. For example, ATARC AST. But no combination of these basic product states can add up to our Bell state BAS plus, because the Bell state contains the PAU and WAS terms but no WAU or AC terms. It's a superposition of two product states. This is the source of entanglement. It's a linear algebra property that comes directly from the nature of the tensor product. It's just a specific vector in a high-dimensional space. Our final example in this section is to see the effect of entanglement during a measurement. Let's work with a slightly different Bell state, often called the singlet state. The singlet state is 1 over the square root of 2 times atoms minus 1. This state is symmetric under particle exchange, which is very important in quantum mechanics. Suppose we measure the z-spin of particle A. We apply the sigma z operator only to the first spin. The operator sasik I acts only on the first ket in each pair. Sasik is heat and sasan is ki. This gives us a new state, which is the Bell state, plus plus. Now let's look at the probability of getting each outcome. The possible outcomes are z-spin up for A, corresponding to the state, or z-spin down for A, corresponding to the state at. The probability of measuring spin up for A is the squared magnitude of the coefficient of the Kiesel term, which is 1/2 is 1/2. Similarly, the probability of measuring spin down for A is the squared magnitude of the coefficient of the Kiesel term, which is also 1/2 is 1/2. The result for particle A is random with a 50-50 chance. But here's the kicker. The state of the system after the measurement is not the original singlet state. If you measured spin up for A, the system collapses to the state. And if you measured spin down for A, it collapses to the state. Notice the consequence. If you measured spin up for A, you know with 100% certainty that if you were to measure spin B, it would be spin down. The measurement on A instantly changed the possibilities for B, even if B is light years away. This is the source of all the mystery. But it's not a mystery when viewed through the lens of tensor products and projection in a 4-dimensional vector space. It's just a property of that specific vector. Let's quickly recap what we've covered and then conclude. First, quantum states are vectors. Superposition is just vector addition. So, a quantum state is a vector, and superposition is just vector addition. Second, observables or measurable quantities are matrices. Observables are matrices. And physics is all about how these matrices act on our vectors. Third, quantum measurement is an eigenvalue problem. The eigenvalues are the only possible results. Measurement is an eigenvalue problem. The eigenvalues are the only possible results you can ever measure. Fourth, quantum probability comes from the geometry of state vectors, specifically the length of their projections onto the eigenstates. Probability is geometry. It comes from the squared projection of the state vector onto the eigenstate. Fifth, time evolution is described by a linear differential equation solved using matrix exponentials. Engineers do this every day. Time evolution is linear systems theory. Quantum dynamics is just matrix exponentials. And finally, entanglement, which seems so mysterious, is a direct consequence of using tensor products to build the vector space for multi-particle systems. Quantum mechanics doesn't need interpretation first. It needs linear algebra. Once you learn the math, the mystery disappears. The weirdness is replaced with an elegant, precise, and powerful mathematical framework for describing reality. I hope this guide has been helpful. Thank you for watching. Quantum mechanics isn't weird. What's weird is how badly it's taught. If quantum mechanics feels mystical, confusing, or philosophical, that's not physics. It's a linear algebra problem you never fully understood. In quantum mechanics, a system is not a number. It's not a position. It's a vector. A quantum state lives in a complex vector space. Superposition isn't magic. It's vector addition. Every measurable quantity in quantum mechanics is a matrix. Energy, momentum, position. Physics happens when matrices act on vectors. No matrices, no physics. Measurement is not mysterious. It's an eigenvalue problem. When you measure something, you are asking, which eigenvalue does this operator return? If you understand eigenvectors, quantum measurement stops being scary. Quantum probability doesn't come from randomness. It comes from geometry. Measurement is projection. Probability is the squared length of that projection. This is just a dot product. Calm down. The Schrödinger equation looks exotic. It isn't. It's a linear differential equation with a matrix. Quantum dynamics is matrix exponentials. Engineers do this every day. Entanglement isn't magic. It's what happens when vector spaces get big. Tensor products don't add dimensions, they explode them. Most quantum weirdness is high-dimensional linear algebra. Quantum mechanics doesn't need interpretation first. It needs linear algebra. Learn the math, and the mystery disappears.